Okay, we're finally here at the last video of the section. 9 videos in this module 6.04. Guys, if you made it, you watched all 9 of these videos and you finally made it to this video, I'm proud of you. Good job. Um, I hope these videos are helpful and worth your time and you're actually learning this stuff in the midst of this strange time that we live in right now. Okay, this last one will be easy. We're literally just doing adding and subtracting vectors and then finding the dot product of vectors in 3 dimensions, and it's very similar to how it's done in 2 dimensions. It's exactly how you think it would go. But I just want to show you so that you have this to go off of. Okay, so we're given 2 vectors, u and v, and we are to find their sum, and we are to find this composition of those vectors, and then finally we'll find the dot product of those vectors, okay? And it goes, like I said, a lot like it does with 2-dimensional vectors. Okay, first thing we notice is that these vectors are not written in their component form. They are written as a combination, linear combination of the standard unit vectors. I, remember, is the unit vector in the x direction, j is in the y direction, and k is in the z direction. Okay, so we have x, y, and z components. Why don't we just write these in in component form, so that we're not confused. Okay? Anytime you see an I, J, and K, you can rewrite it in component form. So we'll go 4 units in the X direction, -1 unit in the Y direction, and 2 units in the Z direction. And then V, we have -3 units in the X direction, no units in the Y direction since there's no J vector component, right? So 0, and then -5 units in the Z direction. Okay, now let's find u plus v. Remember, what is adding vectors doing? When we take vector u and adding on vector v is like taking vector v and taking the tail end. So I travel along vector u, and from that point I travel along vector v. Where I end up is where I would end up if I traveled along the vector u plus v in just one shot. Okay, so u plus v, we just add the x, y, and z components of u and v. So u plus v would equal the sum of 4 and -3, 1, and then the y, -1 plus 0, and then the z, 2 plus -5. So this is the vector u plus v. If I wanted to travel along this vector and then that vector, the shortcut would be to just travel along the sum. Okay. Let's move on to part B. 2 times vector u minus 3 times vector v. What's this doing in space? So if I start at the beginning point of vector u and I travel along vector u twice, so this vector is 2u, right? That's what happens when you double a vector, you double its magnitude. Okay, and then rather than traveling along, let's suppose vector v goes this way, that would be v. I'm going opposite of the direction of v 3 times. So that would be like going 1, 2, 3 v's, a negative v, negative v, negative v. Okay, so this vector right here is the result, 2u minus 3v, is the result of traveling in two vectors in the u direction at the u magnitude, and then 3 vectors in the v magnitude, but in the opposite direction of v. That's the minus. Okay, so this is what we're calculating, is what's this vector. Okay, so 2u minus 3v. First, let's find 2u. 2u would be double of the u vector. Okay, there's u. We just double that. So that's going to be 8, -2, 4. And let's find -3v. -3 times the v vector. So that would be 9, 0, +15. Right? And so now I just need to take 2u, add it to -3v. I just add these 2 vectors together. So 2u minus 3v will give me 8 plus 9, 17, -2 plus 0, 4 plus 15, 19. So that's that resulting vector that we get when we travel 2 u's and then -3 v's. That's that vector that we get. Okay, the dot product. Dot product works the same way in 3 dimensions as it does in 2 dimensions. And since you can't see both the vectors and the work at the same time, I'm just going to copy these down. U is this vector for -1, 2. So we can see everything at once here. Okay, so how do we find the dot product? Same as in 2D, guys. You take the product of the x components the product of the y components, the product of the z components, and you add all that together. Okay, so u dot v equals 4 times -3. I'll just show all my work here. Plus -1 times 0 plus 2 times -5. So that's going to be -12 plus 0 plus -10 or -22. There's the dot product. And the dot product is just as useful in 3 dimensions as it is in 2 dimensions. We still have this formula. Suppose you wanted to find the angle between 2 vectors. Well, then the cosine of that angle is u dot v divided by the magnitude of u times the magnitude of v. And we already know how to find the magnitude of 3D vectors and how to find the dot product now of 3D vectors. It's the same deal. So 2 vectors in 3D space, you can still find the angle between them using this formula. So everything that is done in 2 dimensions is done the same in 3 dimensions. You just have this third component to do as well. Okay, there it is. You made it through the series. Good luck on those homework problems. Please hit me up if you've got questions or need additional help. See me in Zoom. And then good luck on that quiz. I am going to start right now recording videos for the next section on polar coordinates. And I will see you guys there. Bye.